Hi everyone, Mr. Coxford here. Today we're going to be talking about Ohm's law. And to start, we need to look at the journey of a typical electron. Let's remember that when we're talking about the flow of charges in a circuit, it's really electrons that are flowing in a circuit, even though when we're talking about conventional current, we talk about the fact that positive charges are flowing, which isn't actually true, but that's just the convention. But let's just think in general, some charges are flowing through a circuit and they have energy. When they're flowing through the circuit, that energy is going to be lost in a variety of ways. Typically, and most of the energy that those particles possess are going to be lost through something called a load. And now a load could be a variety of things. It could be something like a light bulb. It could be a motor. It could be your fridge. It could be something as simple as something called a resistor. Which has links to something called resistance. A resistor is just a very general type of load. And that energy then is often transformed into some other type of energy, most of the time a useful form of energy, right? To turn on that light bulb or to power your fridge. Also, some of that energy is going to be lost as the particles are flowing through the wires. There's going to be small amounts of collisions between those particles, and there's going to be some energy lost there, but that's a tiny amount compared to the amount that's lost in the loads. Now, every time that an electron or a particle passes through some load, there's going to be a loss of energy, a loss of potential energy. We call that a voltage drop, as we've heard before. Now we have to understand something called resistance. What is resistance? What does resistance come from? What are the factors involved in resistance? Well, resistance is the hindrance or the opposition to current flow in an electric circuit, the resistance of the flow of charges within a circuit. And there are three factors that are going to affect the amount of electrical resistance that some load has. The first is the total length of the load. So how long is that resistor, that resistance that the charges are trying to flow through? And how does that affect it? Well, let's just think. If it's longer, that means that the further that electrons have to travel while being opposed means there's going to be more resistance. And I like to think about this in terms of water slide. We've talked about water slide as an analogy before. So I like to think of this as if we're going to go from the top, we climb up a bunch of stairs, and there's two options for water slides. There's one water slide on the right-hand side where it winds down. It's a nice windy water slide, and it makes it all the way down to the bottom. And there's another water slide that's just a straight drop down. Which one is going to have a faster flow? Which one is going to allow the people going down the water slides to get down to the bottom faster? And it's the one with the shorter path, the shorter water slide, right? So, right, we can think a winding water slide versus a drop. The next thing that affects the amount of electrical resistance in a load is the cross-sectional area. How big or how small is the area that the charges, the electrons, have to flow through? The wider the path, the more electrons can pass through. In terms of water slide, think we have a nice wide open water slide. Lots of water can flow down it. And if we have a super narrow water slide, less water is going to be able to flow down there, right? A wide water slide versus a narrow water slide. And the third factor that is involved in the electrical resistance of a load is the material that that load is made out of. And there are certain materials that allow charges to flow through them a lot easier than other materials. We call this conductivity. They're better conductors. They have a better electrical conductivity. So some materials are better conductors than others. Better conductors allow electrons to move easier. Some examples of good conductors. Good conductors. Metals in general are good conductors, but some of the best conductors are copper and silver. So these are materials that allow electrons to flow very easily through them. Some bad conductors. Glass and rubber, very bad conductors. They are very good at preventing electrons from flowing through them. In fact, we don't even call those conductors, we call those insulators. They insulate, they prevent, they stop the flow of electrons. In terms of our water slide analogy, if we're talking about the material that is made of, the material the water slide is made of, maybe it's nice to go down a smooth water slide, right? You can flow a lot faster down a smooth water slide versus a rough water slide. If you've ever gone down a rough water slide, you probably don't want to repeat that experience. It slows you down and it hurts, right? Okay, now let's get to Ohm's law. Ohm's law is the relationship between the voltage, the current, and the resistance in a circuit. The voltage being how much energy per charge, how much charge the particles in a circuit are getting, current being the flow of charges in a circuit, and resistance being that hindrance to the flow. How are they related? Well, here we have an equation right here that shows us how they are related. V is equal to I times R. Voltage is equal to current times resistance. V, voltage, is measured in volts. That's our unit. Current, I, is measured in amps or amperes. And R, our resistance, is measured in ohms. This symbol here, it's the little omega symbol. It stands for ohms. We just like we could have milliamps and kilovolts and any metric prefix in front of volts and amps, we can have the same thing for ohms. You could have kilo ohms or milliohms or mega ohms. It's a metric unit, so we can have metric prefixes in front of it. This Ohm's law is actually better written in this form. I is equal to V over R. Current is equal to voltage over resistance. And that's because this speaks to the relationship between the voltage and the resistance and how that affects the current. The current is affected by the voltage of the circuit and the resistance of the circuit. And if we think back to our Ohm's Law lab, we see that as we increase the voltage, we have more current, we have a faster flow of electrons, and if we reduce the voltage, we have less current, less flow of charges. Similarly, or inversely, I guess, if we increase the resistance, we have a decrease in current, and if we decrease the resistance, we have an increase in current. And so writing the equation in this form, I is equal to V over R, we can see that current, change colors here, current is proportional to voltage. This means that as the voltage increases, the current will increase, and as the voltage decreases, the current will decrease. It's directly proportional to the voltage. And we can see that current is inversely proportional to the resistance, which means that as the resistance increases, the current will decrease, and as the resistance decreases, the current will increase. The last thing we want to talk about is the power in a circuit, and in fact, the power that is consumed by a load, by some sort of resistance. We talked in the previous section that the power supplied by a battery is the current times the voltage. We derived that expression. So we're going to use that expression, and we're going to use Ohm's law, and we're going to derive two more equations for the power that is consumed by some sort of circuit element, by some load. So let's start here. Power is equal to voltage times current. And we're going to sub in Ohm's law. V is equal to IR. What we're going to get is that we're going to get IR instead of V times I. And we end up with I squared times R. So this is one expression for the power consumed by a circuit element. P is equal to I squared R. It says that if we know the resistance of a load and we know the current flowing through it, we can take that current squared multiplied by the resistance and we get the power. In a similar vein, the power can also be related to the voltage and the resistance. And we can do that by, instead of subbing in for voltage, we can sub in for current. Ohm's law says that current is voltage divided by resistance. So by subbing that in, we can say that voltage times voltage over resistance is equal to voltage squared over resistance. So we have another expression for power. The power consumed by a load is the voltage drop across that load divided by the resistance of that load. Okay, that's it for Ohm's law.